Hello, hello. So today we are going to see how to fine-tune a YOLOX model. We have seen, probably was the last video I shown how to fine-tune a Ultralytics YOLO model. And YOLOX, it's a good alternative. It's a different architecture, and probably one of the main reasons why I would use YOLOX is because the license compared to Ultralytics. So Ultralytics, when doing experiment, is my go-to, and they have great tooling, and fine-tuning is really easy. YOLOX, but the license, it's AGPL, and YOLOX, the license is Apache 2. So also my library YOLO Elixir, which is a library that makes really easy to load and run YOLO models like Ultralytics and YOLOX models, and to use these models in the Elixir environment. Also, my library is under Apache 2. So the advantage of this license is that it is quite open. So basically, you see here, you have already trained models. These are all trained on the Coco dataset. So here you have 80 object categories, the classic 80 object categories, and oh, by the way, this is the website, and you can download the dataset, and you can use it to train your own models, not just object detection, but some other vision models if you want. But these models are, you see, different sizes like Ultralytics, and you can download the weights. You can also use the weights and the architecture for your private and commercial use without having to release to open the code like is for Ultralytics if you choose to follow the AGPL instead of buying the enterprise license. So I think YOLOX is a pretty good alternative. Is unfortunately not that straightforward to fine-tune the model. Reason why I wanted to make this video, especially this is probably a note to my future self when I will forget how to train these models. And another advantage of this model is if you want to use these models on a Raspberry Pi with the Halo 8L or Halo 8 AI hat, you need to compile these models you need to compile and quantize and compile these models to the Halo format, HEF format. And I've found that compiling, quantizing and compiling the YOLOX to me was much easier than the Ultralytics models. In future videos, I will probably show that part if you are into running these models on Raspberry Pi, on that kind of devices. But yeah, so let's go back here and let's start with the with what we are going to do today. So fine-tuning these models, probably we are going to fine-tune, the S model, because I'm going to use these models in future videos, like as I said, Raspberry Pi 5 with the Halo AI accelerator. So the data set we're going to use is this one, license plate recognition. So the idea is to have a full pipeline that what I want to do is to have a full pipeline that detects the car plates. Right now I'm in Europe, Italy, so I need a a good data set that also is able to recognize the European, well, in my case especially the European care plates. And so the YOLO part is to detect, to get a bounding box on where the one or many car plates are. So you get the location. And then we need an OCR, a fast one. And there are many solutions. And again, this is part of other videos. But if you want to see, this is a great model. This is a transformer. But I'm going to probably show you how to make a simple CNN, convolutional neural network, from scratch to do this OCR. So to get an image, you see here that you don't get the full image with all the cars. You get like the image with just the plate. And so we need first to, you see here, to detect in the image where the plate is, and then we run the other model, the other part of the model with the OCR. So let's focus on this, and we are, as I said, use YOLOX, YOLOXS. Okay. So first we need a machine with an NVIDIA. Well, actually, you don't need an NVIDIA, a GPU, but for sure it will make the training much faster. So here I'm going to use an instance that Glisses gave me. So thanks a lot again, Glisses. I'm using these instances this type of instance with an NVIDIA L4DS to fine-tune this kind of models. I have a 46 gigabytes of GPU RAM. And we're going to first download this repo. Okay, so first, let's see the Python version I have. Right now I have 3.11. If you have Python 3.12 or later, I think it's better to downgrade it or to install a different Python version with, well, I used a SDF. And currently installed 3.11 or earlier, because the requirements here, there are some issues. If you try to install these dependencies and YOLOX, you're going to have some issues. First with the ONNX simplifier, then Torch. If you install Torch 2, I think it's not supported by YOLOX, and yeah, it's far easier to install Python 3.11. So YOLOX you have here inside the library, and here the dependencies. But first I'm going to create a virtual environment just to isolate everything inside here. Okay, and then what I want is to first install the requirements. This is the original file, okay? So let's see what happens. It should fail, you see here. And the reason is, let me see if it's visible. Yeah, here you see that it's trying ONNX simplifier 0410. So what we need to do is to downgrade it to 310. All right, so yeah, here I have some cache stuff because I already tried a few things. Great. We have our requirements installed, but now we need to install YOLOX. And let's see. Yeah, there is another issue with Torch. So what we need to do is to install Torch 1.13.1. Okay. Okay, and then if we install it, if we install here, I'm installing YOLOX, it should work. Here is removing Torch, installing again Torch. I don't know. I mean, here is uninstalling 1.13 and installing back to 8. Yeah. But this should work. Okay. Yeah, you see here it installed back to 8. Yeah. So to see if it works, here we have tools, train, which is the script we are going to use, help. And yeah, then there are so let's close these, and then there are there is the data set, and we're going to use this. So here are some American license plates, also of some bikes, but inside here I've seen also some European, let's see if I can find some European license plate. This should be a UK. No, let me see. I'm pretty sure I've seen some European plates. Yeah, this. Yeah, you see, this is, I think, Netherlands. So yeah, we have also European license plates. I don't know how many in the but yeah, great. So the point here now is to download the dataset, and as you can see, the we have just one class, okay, which is the license plate. So download project, we are going to download the dataset as a zip file. Really important, the format. So the format, we are going to use the Coco annotation format, and I'm going to show the download code. So let's use this. Okay, finally we should have our license plate here. So I'm going to move it. Yeah, move it here. Let's call it plates zip, and let's unzip it. Okay, so we have a test, train, and valid folder, and we need to, if I remember correctly, we need to rename these folders. So test needs to be renamed with test 2017. Same for train. Train needs to be renamed to train 2017. Valid 2017, and we need to create an annotations folder. So these are the files and the structures, the folder structure that YOLOX expects during training. And inside annotations, you see here these folders. So inside here we have the training images, train. You see that if we count the lines, so here we have around 7,000 images. Okay, so inside train we have annotation calco JSON. So this is a JSON file where we have all the details we need about each image. Let's see if I have JQ. Yeah, so no, let's do annotations, JQ. You see that here there is also, if I remember correctly, there should be an annotations array. Yeah, it's this one, which inside we have the image ID and the information of the bounding boxes, and the images. So you have two separate arrays. You have the images array, which inside you have the information about the images, resolution, etc., and then you have the annotations. So which are the annotations on that refers to the image IDs you see here. Image ID. Great. And we need to move the train annotation, this JSON file here, inside annotations. Now I need to remember actually. So yeah, it should be train annotations coco JSON. Same thing for the valid, so for the validation, annotation, so annotations, valid, or actually, yeah, let's call it val annotation, annotations coco JSON, and then same for test. Okay. Annotations, test, annotations, coco, JSON, yeah. So this is the format that YOLOX expects. These actually, we can set the names of the JSON files, but we need to create inside here, inside this exps folder, which should be experiments. So you see here, go in default. These are the experiments, basically kind of configuration files for let me copy and paste our plates experiment, and as you can see, it's so this is actually kind of a configuration file for the the training, and you see that Dataset is the folder where to find the subfolders, train, validation, and test. Number of classes actually is the reason why I think I've put 2, but let's see later if it were it should be 1. Probably it could be 2 because there is like a super class, always referring like to a car plate, but let's set it to 1 and let's see what happens. And yeah, these are the workers to data, so probably to load the data, but the things you really need to change are these. I'm going to copy and paste this stuff in the article that is linked to this video, and you should find the article like in the description of this video. So let's save it, go to the root YOLOX folder. I'm following some notes here. Oh yeah, something important of the experiment we've just created is the where is it? Plates. So this depth and width. So this is the width and the depth of the of the network. Like saying, okay, it is so you can set 1-on-1. I don't even know if I'm able to. Yeah, probably with this GPU I can train with 1-on-1, but probably I wouldn't be able to move it to compile it and quantize it for the Raspberry Pi. This is the size of the network, okay? And probably you've also seen some here YOLOX S experiments. So yeah, these are other experiments, default experiments for YOLOX models. All right. So to train the model, we first need the weights we want to fine tune, which are the weights of the YOLOX S version. So these weights here. Let's see if I'm able to download these things here. YOLOX S should be a PTH file. Yeah, YOLOX PTH. Yeah. Okay, works. And should be about 30. Oh, actually. Yeah, 69. Okay, 69 megabytes, 70 megabytes. And I don't know. Let's remove this. Okay. So basically, we're going to start from this. So we're going to fine tune this model. Basically, moving from the 80 classes to one class, and then fine-tune all the weights based on the data we have here in the data sets. The cool thing about fine-tuning, as I said in the other video, is that we don't need as much data as we need when training a model like this from scratch, because we are using the embedded knowledge, the knowledge that is already embedded in these weights, and this model has been trained, as I said, with on the Coco dataset, which is massive compared to our dataset here. Great, let's try to train it. So tools, train is our command, is our script, training script. F plates. So this is our experiment. D1 is the GPU device. 64 is the batch. So the system loads the data in batches, and it runs the optimizer, probably Atom or gradient descent, in batches of 64 images per time. And here the checkpoint is where actually we start from, YOLOX, these weights here. Let's see if it works. Doesn't contain class exp first, is it? Does it find it? let me copy. Actually, let me move it from default plates to here. And let me see if, okay. And let me see if the file should be in the root folder. Yeah, that was the reason. So plates should be in the root folder. Let's see here. Probably this is going to have an error at certain point. Let's see. Okay. Core dump. Ooh. What a fuck. So let's see what happens. Okay, the error seems to be caused by this number of classes. So when because originally I put one class, but yeah, there are two classes, and the reason is we have one class because under here dataset you see classes just one, but how the Cocoa annotation is made, let me see, under annotations, for example train here, let me see, there should be categories, or you see here, so we have two categories. One, which is license plates, super category, none. And then we have ID1, license plate, super category, license plates. And most of the annotations, actually all the annotations, they use this. So we could delete, so you see that there are two categories here, but just one is used because there is this super category and category. Probably they need this. The training, the Cocoa dataset is exported. This file is exported with this format of two categories with super category. I don't know, but what we can do, and what I did when it worked, because obviously I already tried, what I'm trying to show you is to just delete the root category. You better use CyberDoc. I'm going inside here, dataset annotations. So let's start with test. Let's format the document. So you see here, categories. Let's remove this. ID1 is fine. None. Plate. Let's call it plate. And actually, if we go here, you see that category 1. The important thing is that just category 1 is used, because if category 0, ID 0 is used, obviously we will get some errors. So yeah, category 1, great. When we save, CyberDoc is going to save the file remotely. So validation. Where is edit with code? Yeah, I prefer to format. Same thing. Super category, none, and let's call it plate. Save it. I already removed. Yeah, already done. Just call it plate. Okay. We are ready to train our. So let's remove this YOLOX outputs and let's start again. So train plates, batch of 64 images, and let's go. Almost 9 million parameters. And you should start to train the model. Let's see here. You see here. So this is the first epoch. So we have this error, and is when running this. So val 2017. Let's see first. Yeah, we called valid 2017. So yeah, the val 2017. We need to rename. So when running the validation after the first epoch, when running the validation to see the metrics with on the validation data set, on the validation set, it didn't find the directory. So let's start again. I'm using screen to start the watch NVIDIA SMI. So we see that we're using the full GPU, and let's create another. So watch free. So we are using. Okay, let me see with top. And let's see the metrics. So here, this is the first epoch. 111 iterations, meaning 64 is the batch of images times 111. It's around 7,000. Okay, so there is this error, and I knew this was coming. Yeah, this is because. So let's see inside plates. Yeah. So it's because we have still two classes here. We need to set it to one class. So here I finished. Probably we needed less than 30 epochs to reach this result. But yeah, so probably 10 epochs were more than fine. But yeah, you see that best average precision is 69.03. So let's just a comment on and consideration on the metrics here and how to understand what these metrics are. I said a little bit what these IOU means and MAP. When you see, let me show you here, MAP at 50 means mean average precision with an IOU of 50%. You see here, which is equal to the mean of the average precision metric across all the classes. We just have one class here in a model at 50% IOU. IOU is, well, the acronym is intersection over union. Basically, what this means is that, as I said before, let's get one image to. So the model predicts a bounding box, and IOU of 50% means that the bounding box needs to have an IOU of at least 50% IOU, meaning it's kind of a score to understand the overlap. We can consider it just to simplify it. So it's intersection over union. So it's how close this our bounding box is to this bounding, the real bounding box here. Okay, so if there is enough overlap, well, at least 50%, we get it's considered okay. If not, it's considered an error, so false prediction. So when going back here to the terminal, so we have many mean, AP, AR. So let's focus just on mean average precision here, 6903. But why here we have 96.8 and why I was watching at this? Because this is, you see, IOU 50% is this one, is the one here in the that you see here under the matrix for the model they trained. They reached 97.2, which is higher, just a bit higher. I don't know the model size, honestly. Let me see. Probably it's possible to see here the model. I don't know. It would be interesting to see the model they trained. But yeah, it's not now the okay, this is not a YOLO. This is the model type. This is I think RoboFlow has written a paper about this model. Actually, I think they created this model. It's I think it's a transformer. But yeah, I'm going a little bit on another topic here. But yeah, the matrix. So let's focus. We can focus on this. But obviously, this is the less. So this is not a strict metric. If we want, so the most strict is this one. Well, no, it's not the most strict, sorry, but it's an average of different IOUs. So what it does is calculate the MAP of a mean average precision at an IOU with an IOU of 50%, I think then 75, 95%, maybe there are some other IOUs in the middle, but the point is it calculates until 95%, which is the most strict, and then this is an average. Now that we have our model, we have it here under YOLOX, YOLOX outputs, plates. We have different checkpoints. Actually, I think one checkpoint for each epoch. We want best. Okay, we have it here, but as you can see, it's still a Python PyTorch file with the weights. We want to export it to ONNX. So let's use Python tools. Under tools, we have export ONNX. Let's see if there is a help here with the different. Okay, we're going to use C, which is for the checkpoint. Where is C? Here. It's our the weights of our fine-tuned model, and then the batch size. So we how big is the input batch size? It's going to be 1. Especially because we are thinking to use just 1 frame per evaluation. And the offset, this is the ONNX offset. We are going to use 12. And we need, again, the exp file, the which is plates here. So Python tools, export ONNX, and batch is batch size 1, f plates pi 012. Probably there would be, I think, a problem with this. Oh yeah, okay. So you see here weights only. We need to make a small change in the code of the file here in the tools in the export. So yeah, this is why I think it's not really maintained, this project. Well, also because if you see the number of issues and pull requests, I mean, they piled up. So there should be somewhere here, torch, ONNX. So first, export. Let me see if there is a wait. Torch load here. Okay, I think it refers to that because argument in torch load. So waits only from false to true. We want waits only false. Okay. And let's save and see if it now works. And let's use plates.py to see if the local file in the root folder works. Okay, this is another thing. It's we need to be because here export needs to be this function needs to be we need to use the export function. It should be as easy as this. And that's it. I think it worked. Let me see. I think we should have, you see here, this YOLOX dot ONNX is our ONNX file. Okay. So let's see how our model works. So we have the YOLOX output plates, and then the best checkpoint here. And so to evaluate, we can do it on an image, but it's boring. I mean, it's far better to use something like this. So there are many videos on YouTube. You can find these videos, and these are dashcam videos of just driving into the traffic of different cities here in London. So my two tests I'm doing just to have a feeling of how it works is to use these two videos, but there are many other videos, and just obviously like a minute. You can choose, you can take a look of different situations. Obviously, it's more interesting to see different situations. But so the cool thing is that both YOLOX and Ultralytics, they give you some scripts to run these models on videos like this. Basically, they go through each frame and run the detection, and the output frame will have the bounding boxes with probabilities. Obviously, it works also with other models, and when you have different objects, you will also have different labels. So how to do it? There is a tools demo script here, and to use it, you have also to make a change. So there is, if I remember correctly, there is a torch load. I already edited this. You see here, weights only. You need to add this weights only false. And it's the only thing you actually need to really run this demo script. But if you want, because this demo script is built around the Cocoa dataset, you see here that it's using Cocoa classes. If you go at the end of the script, you will see here that you run the predictor, and then as the third argument of the function is tuple. So this, for example, Cocoa classes, you have many elements of the tuple. In our case, we just need to pass the plate, and that's it. So now we can run Python tools demo, and we have, for example, London traffic trimmed to. So I have many videos where I tried different models. So for example, this like London traffic trimmed .mp4, and we run tools demo. So first, our plates.py, where we have the model configuration, well, the training and the model configuration. Then the weights, so the checkpoint. So YOLOX. Let me copy and paste from my notes here. So the best checkpoint. Then we have the path of the video, London traffic. So this is the long one, trimmed. It's still long, but. And here are the confidence threshold. So here, to make things interesting, I'm going to use 25%. So at least a 25%. It seems a low confidence, but it filters out most of the time 25%. Over 25%, it's a good confidence. But obviously you will see that we will sometimes see that a plate like it detects traffic signs like plates. So obviously playing with this, you with a higher confidence, like 50-60%, you get you're definitely more confident. You get better result, better accuracy, but you get also less detections. And sometimes, well, actually many times, when a plate is really far away, you get a lower confidence, something like 0.3, which means 30%. You need to play with those parameters. And NMS, which is non-max suppression, this is to filter out duplicates, and 45%, 50%, it's good. T size, and I'm going to play with this later in the evaluation when I'm going to see the result. But a 640, it's a good one. It's a good one. Well, we trained the model with 640 input, 640 by 640. So all the images have been resized to 640 by 640 using padding. Most of the time, this model, the deeper processing doesn't alter the ratio. So it adds padding. 640 by 640. If you have a 4K video, it's resized to 640 by 640. So things like small plates become pixels, and you can use our small model. You can use it even if it has been trained with 640 by 640. You can use it with a 1280, for example, input, and this is a cool thing we can do with convolutional neural network. Even if the network has been trained with different input, we can change the input size, and what it means is that if the architecture is done correctly, we will have more detections. This is maybe something I can show you in a different video. T size 640, and then device GPU and save result. Save result meaning you will find the output video here under YOLOX outputs plates, and that's it. What else? The demo arguments are required. Demo. Oh yeah, video. So I think we need video here. And it starts to run the inference for each frame. So let's see the result. I have trained a few models, different models with different sizes, even ultralytics, and I have here the same video with the different results, so we can see a little bit what's the difference. So I think that without having to, we just have around 10,000 images, and I think the results are pretty good. And we can try different models, and as you will see, the larger models, the X, we also have here the small model, but also we have the extra large model, which is 10 times larger. You can get better result, better confidence in the detection, but this is useful until a certain point. You can tweak and play with the models, but most of the time it's better, and it's easier to have better data and more data to train the model. This most of the time gives better results rather than stay there with larger models, but a small data set. So what you will see here is, well, as you can see, the demo script. This is the result of the demo script. You have the same also with ultralytics. You can do the same. We will see later a video with that result. And as you can see here, we have the bounding box with the probability, the confidence you see here. And you see that we're able to see that here there is a plate, as humans. So here it's cool that it detects immediately the plate, but you see that here, as soon as they are far away, they're not able, the model doesn't detect those two, basically because the confidence drops much below 25%. Well, if we go in a larger model and we go in the same position here, so this is the extra large model, and the input is 1280. So the frames are resized to 1280 by 1280 instead of 640 by 640. This helps, but not as much as having a larger model. It depends also from the data set you have. So as you can see, in a similar scenario where we have, so you see here, 26 seconds, I don't know, this, but yeah, in similar scenario, it's able to detect the two core plates, even with high confidence, more than 50%. And well, the reason is because so the dataset is the same. I trained this even with less epochs, 10 epochs, and the dataset is the same. The number of parameters is 99 million, so larger model, larger input size, and but there are sometimes there are issues, like for example, you see here that it detects this light as a plate, probably because there is so this is the large model, and even the you see that just by 0.6% is over 25% confidence. So, but yeah, this is an error, and I don't know if it detects. It doesn't detect this plate here, but it's able to detect these plates that are far away. And this model has issues, similar issues, but is able to detect this plate. And probably doesn't detect this one. Yeah, but when it's close. And remember the matrix. We got the worst mean average precision was on the small areas. So consider that these these frames are resized to 640 by 640. So this a screencast. I'm recording this as a it's probably 180p. So this is resized, and these plates are much smaller when they get processed by the model. So yeah, it's normal that plates that are far away, they are not detected, and just when we go close to these plates, we're able to detect them. And even if sometime we're able to detect the plates that are far away, what do we do? What can we do with that information? If the source, the original video, I mean, if we are not able to distinguish the letters and numbers in the plate, we don't even, I mean, even if we detect the plates, we don't have any information that could be useful if we want to run a plate OCR. And yeah, and then here I have another video just to show US. This is New York, so this US plates, and this is extra large model. So again, 99 million parameters, and I've seen something interesting. For example, this has been detected as a plate, and also this, as you will see, this will be detected. It's good. It's doing a great job here to detect all these plates. Really good job. I mean, we're using a public dataset that is just, the training was only 7,000 images. I mean, at least we need more data to higher the accuracy. That's for sure. But yeah, this is detected as a plate, but it works pretty well, all considering. Okay. So that's it for this video, and let me know if you're I originally thought to make this video like really short, but I tend to add a lot of details, like for example all the comments, as you saw if you reached the end of this video. And I tend to add a lot of comments, opinions on models, metrics. This is something I really like, and probably would be better to do some videos just about comparing the models or showing the architecture. Just let me know in the video, in the comments below, if you're interested about these details. And yeah, and let me know if you want something specific about object detection. Bye.